For over a century, humanity has been wrapping the Earth in an invisible blanket, woven from more than 1 trillion tons of carbon dioxide. This has fundamentally altered our planet's climate system. And while we're finally getting serious about cutting emissions, we face a difficult truth. Simply turning off the industrial tap is no longer enough. The sheer volume of this legacy CO2 has locked us into an atmospheric carbon bottleneck. This means that even if we achieved global net zero emissions tomorrow, the climate consequences of our past actions, the increasingly frequent extreme weather, the steady rise of our oceans, will continue to worsen for centuries. To avert the worst impacts and stabilize our planet, we must not only stop emitting, but actively begin to clean the sky, removing gigatons of carbon directly from the air. This is the core mission of direct air capture, or DAC. You can think of it as a giant chemical filter for the atmosphere, or an industrial tree on hyperdrive. The process starts by drawing in massive quantities of ambient air. Inside a DAC facility, this air passes over large contactors coated with specialized chemical sorbents. These can be either liquid solutions or solid materials. These sorbents are engineered to act like a molecular magnet, selectively binding with CO2 molecules while letting other gases like nitrogen and oxygen pass through untouched. Once the sorbent is saturated with carbon dioxide, it's heated in a controlled process. This heat causes the sorbent to release the CO2 as a pure, concentrated stream. From there, this captured carbon can be permanently sequestered thousands of feet underground in stable geological formations. The strategic power here is that DAC is location agnostic. It can be deployed anywhere with access to renewable energy and suitable geology, making it a uniquely flexible cleanup tool. However, scaling this technology to the gigaton goal, removing billions of tons of CO2 per year, presents immense challenges. The first is energy intensity. Moving and processing vast volumes of air and then regenerating the sorbents with heat requires a significant amount of power, which must be zero carbon to be effective. The second is cost. Today, removing 1 ton of CO2 from the atmosphere costs anywhere from $600 to $1,000. To make a real impact, we need to drive that price down dramatically. This demands a revolution in innovation, developing more durable and efficient sorbents, integrating waste heat from other industrial processes, and using modular manufacturing to scale up production. It also requires robust policy support, like carbon pricing and direct government procurement, to create a reliable market. Direct air capture is not a silver bullet that excuses continued emissions. It is an indispensable safety net, a critical tool that provides a pathway to achieve true net negative emissions, buying us vital time to build a sustainable global economy.